Hello, my name is Ushnishan Gupta. I'm a PhD student in the Department of Engineering, University of Cambridge. Today I will be presenting joint work with the German Aerospace Center in Lampoldshausen on avoiding thermoacoustic instabilities in cryogenic rocket engines using Bayesian deep learning. Positive feedback is great when dealing with people, not so much when dealing with combustors. Thermoacoustic instabilities can occur when a positive feedback loop is set up between acoustic waves and heat release rate fluctuations at the flame. An acoustic wave incident on a flame can cause heat release rate perturbations, which in turn generate more acoustic waves, and so on. If the relative phase of the heat release rate fluctuations and the acoustic waves is favorable, then this quickly leads to large amplitude oscillations within the combustion chamber. In the laboratory setting, thermoacoustic instabilities simply produce a loud tonal noise that annoys all the PhD students sitting upstairs from my lab. In high energy density combustors, however, such as those found in rocket engines or aircraft engines, the consequences can be far more severe. Structural damage can result either directly via mechanical means from the high amplitude pressure oscillations, or due to enhanced heat transfer through the chamber walls during instability episodes, which can result in material failure. In this study, we use experimental data from the BKD combustor operated by the German Aerospace Center. BKD is a cryogenic rocket thrust chamber whose thermal power output at maximum chamber pressure is comparable to the power consumption of a small town. Operating conditions are representative of European industrial liquid oxygen hydrogen engines such as Vulcain or Vinci. It was originally designed to study regenerative cooling of liquid hydrogen, but thermoacoustic instabilities cropped up during early testing. Following this serendipitous discovery, researchers in the German Aerospace Center decided to make lemonade out of lemons, and BKD is now used as a research platform for thermoacoustics instead. It is equipped with a variety of sensors, including static pressure sensors, multiple high-frequency dynamic pressure sensors, optical fibers, thermocouples, etc. The picture on the left shows a typical experimental run on BKD. At high chamber pressures and high ratios of oxidizer to fuel, the first tangential acoustic mode of the combustion chamber is excited. This is clearly visible in the 10 kHz area of the dynamic pressure signal spectrogram as an angry red line. In this study, we are using data from 5 such experimental runs where these instabilities pop up. Engineers have a few options if their combustor is thermoacoustically unstable. The first and best defense is a design modification, such as a change in the geometry, addition of dampers, baffles, or resonators. If the system still becomes thermoacoustically unstable under certain conditions, then we retreat to our second wall of defense, which is avoiding unstable conditions. To do this, the engine controller needs a reliable algorithm that can forecast instabilities in real time. Consequently, finding precursors for instabilities has been a preoccupation of the thermoacoustic instability community. Different authors have suggested different measures of stability, which has resulted in a veritable zoo of instability precursors derived either from pressure measurements or optical chemiluminescence measurements. The first steps were taken by Leuven, who derived a stability margin for the combustor using the autocorrelation decay in the measured combustion noise. Gotoda and co-workers suggested that when a combustor becomes unstable, there is a transition from chaotic to deterministic behavior, and used the Weyland test for nonlinear determinism as a precursor. Nair et al. In their paper had a similar idea, and they applied the Gottwald 01 test for chaos. In later papers, they also applied recurrence quantification analysis and computed the Hurst exponent to obtain precursors. Kobayashi et al. Have computed the synchronization index between pressure measurements and OH chemiluminescence measurements, and also constructed ordinal partition transition networks from pressure and optical measurements for to obtain precursors. In a recent paper, we showed that the power spectrum of combustion noise is a fingerprint of the underlying state of the combustor, and this can be used, among other things, to determine how thermoacoustically stable a combustor is. In this study, we approached this problem of forecasting instabilities by training a nonlinear autoregressive model with exogenous inputs. This is used in machine learning to model dynamical systems where future states are assumed to be a nonlinear function of past states, x, and exogenous variables, u. In our problem, the future state that we need to predict is the probability of the combustor remaining stable within a time horizon of 500 milliseconds. An instability event is defined as the ratio of the pressure fluctuation amplitude and the static pressure exceeding 5%. The exogenous variables u are the two control signals for oxidizer and fuel flow rates, which are varied throughout the experiment. For the state variables x, we are spoilt with options, since BKD has so many sensors. We have the static chamber pressure measurements, pressure and temperature measurements at the fuel or oxidizer injectors, and these can be used as state variables. We also have the 8 high-frequency dynamic pressure sensors spaced equally around the circumference, as well as 10 photomultipliers measuring the intensity of OH radical chemiluminescence. These can then be used to compute measures discussed in the previous slides, and these measures can be used as input state variables too. Finally, the nonlinear function f is modeled as a Bayesian neural network. So why is a Bayesian neural network the appropriate tool for this problem? Machine learning techniques can perform poorly when given inputs dissimilar to those seen during training, so-called out-of-distribution data. This can be problematic for safety-critical systems like rocket engines, particularly since our algorithms will be trained on datasets whose size is necessarily limited by the resource-intensive nature of the experiments. Each experimental campaign on BKD, for example, costs tens of thousands of euros. Bayesian neural networks can quantify predictive uncertainties in small data and medium data settings and make our predictions robust to overconfident extrapolations. A Bayesian neural network starts off with a prior probability distribution over all the parameters. When the network has not observed any data points, its predictions are completely guided by the prior. You can see this in the picture to the left, where the prior distribution implies a highly uncertain, vague relationship between the predictor variable and the predicted variable. Once data points are observed, Bayes' rule can be applied to obtain the updated posterior distribution over parameters. In the picture to the right, we can see that our neural network has now seen the 5 red data points and has updated its predictions to reflect this. Near the observations, it is fairly confident about its predictions, but far away from it, it retains its uncertainty. Our Bayesian neural network has a simple architecture with only 2 hidden layers with 50 units each, since our limited hyperparameter tuning revealed that wider or deeper neural networks do not improve things by much. Because we are working with time series data points are highly correlated with each other, so a random test train split can be misleading. To obtain an honest evaluation of our models, only 4 experimental runs are used for training, and the entirety of the 5th one is held out for testing. We also want to make sure that our model performance is not dependent on which particular experimental run was chosen for testing, so we use leave one out cross-validation and only report the average performance across all 5 possible train test splits. Our NARCS models actually perform quite well. In this example plot, we show the performance of one of the trained models on the held-out test run. The blue curve is the experimental observation. It is equal to 1 if an instability event if an instability event happens in the next 500 milliseconds and 0 if not. The red line is the predicted probability of the system remaining stable. This model used the power spectrum of the dynamic pressure signal and the control variables as its input, and we can clearly see that it successfully forecasts both instability events that occurred during this run. It's interesting that the orange bars, which represent the uncertainty of the Bayesian model, only become visible during the transition events. This is because there is a lot of data in which the combustor is completely stable or completely unstable, so the model is confident in those regions. Transition events, however, are short-lived, which increases the epistemic uncertainty of our Bayesian neural network. Of course, eyeballing the results like this is not sufficient. We need to quantitatively evaluate our models and compare them. To evaluate our binary classification models, we use the area under the ROC curve as a metric. This is simply a plot of the true positive rate versus the false positive rate as the threshold of the classification is varied. The ideal value of this metric is 1 for a perfect classifier. And if we are controlling a rocket engine, we have very little appetite for false positives or false negatives. So we want the area under the curve to be as close to 1 as possible. As discussed in a previous slide, we trained multiple NARCS models with different state variables as inputs. Here, we report the average AUC for some of the different models that we trained. The first model is a naive baseline model, which simply predicts that the state of the system will remain unchanged. If the system is currently stable, it says that it will remain stable in the next 500 milliseconds and vice versa. Now, of course, this is a completely silly and useless model. Nevertheless, it provides some context for the AUC numbers, and any model that pretends to be useful needs to be significantly better than this naive baseline model. Fortunately, all our other models are considerably better with AUCs much closer to 1. The second NARCS model uses the current static chamber pressure, the current pressure and temperatures at the injectors, and the current ratio of oxidizer to fuel as input state variables. It performs well, with an average AUC of 0.9908. The third model uses the average complexity and entropy of the high-frequency dynamic pressure measurements, which according to Hachijo et al. Are excellent precursors of instability, and it performs even better. The fourth model uses the average power spectrum of the previous 100 millisecond of dynamic pressure measurements, and this again is slightly better than the previous model. The final model, and the one that performed best by a small margin, used as its input all the variables from the second model, so the static chamber pressure, injector temperature, ratio of oxidizer to fuel, plus the dynamic pressure power spectrum. In conclusion, we used Bayesian neural networks that use data from multiple sensors as input and are capable of forecasting potential thermoacoustic instabilities in real time. While all the trained models were found to be quite accurate, the models that used information from the dynamic pressure measurements fared best in terms of accuracy. There is still a lot of work that remains to be done. As I speak, we are also evaluating models that use the photomultiplier data as input. We're looking at applying these methods to other datasets like methane oxygen experiments and seeing how well models trained on the current data can be made to generalize to these new settings using transfer learning. More excitingly perhaps, we're looking at implementing these early warning systems on the hardware so that we can evaluate how well they perform online. Thank you for listening, and if you find this project interesting, please feel free to talk to me. I look forward to engaging with you.